All right, good morning, everyone. Welcome to virtual seminars in Precambrian geology. Today, we're hearing from Dr. Latisha Brengman from the University of Minnesota, Duluth. Her talk is going to be on working towards a comprehensive diagenetic model for iron-rich sedimentary rocks. So I will introduce Latisha for us, and we'll go ahead and get going. So Dr. Latisha Brengman is a sedimentologist and biogeochemist. Her research involves detailed fieldwork and petrographic characterization of Precambrian sedimentary rock, combined with geochemical analysis using high spatial resolution techniques. She pursues a variety of questions related to, but not restricted to, the development and evolution of Earth's early biosphere. Latisha received her bachelor's degree in geology from Northwestern University, working on the sulfur isotope composition of the 800-million-year-old Bitter Springs Formation from Australia for her undergraduate thesis. And then her PhD from the University of Tennessee in Knoxville, working with Dr. Chris Feddo. Her thesis titled there was Geochemical and Isotopic Characteristics of Precambrian Primary and Secondary Chert. After her PhD, Latisha worked as a research associate with ExxonMobil and at Wisconsin Geologic Survey. Afterwards, she started as an assistant professor at the University of Minnesota in Duluth, where she has recently become associate professor and continues her research on rocks from the Freedom Formation in Baraboo, Wisconsin, from the Nemicky Basin in northwest Minnesota, the Vermilion District in northern Minnesota, and the Abitibi Greenstone Belt in Canada, all at different times across the from the Archean into the Proterozoic. So it's really great to have you here, Latisha. We're really excited to hear from you. So please go ahead and take it away.
Thanks so much for the introduction and the invitation to talk with you all today. I'm really excited to discuss and to continue to learn from you all. So the topic that I want to talk with you all about is thinking about how we approach diagenesis, particularly in a wide swath of iron-rich chemical sedimentary rocks. We'll focus a little bit on the Proterozoic because of some of the interesting complications that arise with the minerals that we see. Yeah, I'd like to thank, specifically, I'm going to highlight some of Sam Duncanson's work. He's a previous master's student at University of Minnesota, Duluth. And then my colleagues, Athena Eister and Jenna Johnson and Esther Stewart. It certainly wouldn't be possible to talk about any of this material without them. And it definitely wouldn't be possible without lots of drill core records. So I definitely want to thank both the Geologic Surveys of Minnesota and Wisconsin and the Department of Natural Resources. It's a wonderful catalog and archive of information that we get to investigate because it's preserved. So kind of highlighting, there's a lot of mineral categorization that I'll talk about. We'll do the highlights. I tried to keep it a little bit shorter so that we could have a lot of discussion. But I definitely want to thank a lot of the undergraduates and graduate students in the lab who've made this work possible over the years, sort of cataloging the painstaking work of cataloging lots of mineral reactions in lots and lots of drill core and thin sections. I wanted to start out kind of what fascinates me about this type of work and thinking about diagenetic reactions and really post-depositional change is kind of where I started. I started in these systems that have a lot of heterogeneity and they represent really wild disequilibrium. So this is an example of the famous silicified komatiite units, and we see this type of wild disequilibrium in Archean assemblages. And so I started out kind of looking at mapping together in situ tools with bulk work to kind of get a sense of, can we track some of this mineral replacement in a systematic way? And one of the key things that we kind of kept finding is that there's a great degree of heterogeneity. And so a lot of that is decipherable depending on how you approach analyzing different pieces. But at the end of the day, metamorphism and fluid mobility in systems leads to a lot of overprinting, right? So we started to look at more well-behaved systems, or what we had hoped to be more well-behaved systems, and thinking about iron formations that potentially represent this really important archive of past seawater. So here's a beautiful example of an Archean iron formation. You can see the really beautiful microbanding in the sample, and mineralogically it's not incredibly complicated. There's some silicates, a little bit of carbonate, and some oxides. But when we were looking at micro scale heterogeneity, we found it kind of in a lot of the systems we were working with. And so maybe this is because it's Archean, because it's very old. There's lots of things that can go wrong in old terrains. So we started looking in younger terrains across the Proterozoic. And so when I first looked at Archean or Proterozoic iron formations, I was sort of surprised by the great degree of mineralogical heterogeneity that existed. And so you might be thinking, that's not what it's supposed to look like. But when I show you these sort of pictures, there's a lot of change that's happening and that's captured in some of these samples. And this isn't just a representation of like the worst examples I could pick to show you a lot of heterogeneity. This is sort of just generally how a lot of the granular iron formations that are in the Proterozoic that we've been looking at, how they look. What we want to do then, and what kind of I want to motivate this talk with, is there's a lot of really fine scale heterogeneity, mineralogical heterogeneity, that we don't quite have a great key to unlock yet. And so I want to walk you through an attempt to try to build a model for one example of what I think is relatively systematic heterogeneity. And sometimes it can feel a little bit like this GIF that's playing right now because of the great degree of change that we see. So I want to frame the talk as thinking about our overarching goal. It's a path that we're on. It's certainly not complete, but we really want to build a diagenetic framework for iron-rich chemical sedimentary rocks. We have a great one for carbonates, and lots of wonderful folks are working on refining that model for carbonates. And so, in iron-rich chemical sedimentary rocks, we have a long way to go to sort of build a real comprehensive diagenetic framework. The key results you already know from the abstract if you took a look, but the things I want to highlight are, number one, when we look at silica-rich or silicified horizons, they preserve multiple incomplete reaction sequences. And what's really great is that allows us to decipher a relative order of events. The second point that's a key take home is that we're going to find some minor differences in the major and trace element geochemistry, but when we look at redox information preserved in geochemical data from both banded and granular couplets, so grains and sand-sized material and mud-sized material effectively, they record relatively similar redox information for any given depth interval. And then the last point I want to leave with is thinking about an added potential complication of thinking about how reactive are these rocks after they initially form, and sort of how long are they being affected by these post-depositional changes, and how might we better incorporate local element mobility into something like a larger diagenetic framework. So to do that, I want to first set the stage, kind of focusing on the scale of the evidence that we'll talk about today versus sort of the scale of the types of questions we can really answer with it. And I really want to focus on sort of our approach to building this diagenetic model for the samples that we're looking at. And so we'll start by looking at finding and mapping a lot of these incomplete reactions. We'll go through the best of highlights. And we'll look through a relative, being able to put together a relative order of events, but really tying that to mineral reactions that are occurring and that we can document at the micron scale. And then after we do that, we'll apply, through this lens of thinking about textural data and mineral data, we'll apply our geochemical data lens to the same samples. And then I just want to end on sort of a discussion or a thought of how universal versus generalizable any of these types of models might be. So to set the stage, if we really want to tackle this at a large scale, we would really want to do a multi-basin comparison. And so we're not there yet, but we'd want to do something that incorporates a lot of time and a lot of space. And that's because if we're going to think about these large scale questions that many folks are interested across the Precambrian, these fundamental large scale changes, we want to be comparing that at a large scale. We're going to focus for now on thinking about the small scales, the small spatial scale, relatively small time scale, and thinking about can we sort of map out the diagenetic history of units in a really detailed way, such that when we get to looking at multi-basin comparisons, we really have a great idea of how change is happening and how much change is happening. And so we are going to use drill core records, which represent a large scale. We're going to use two localities, not contrasting, two localities, but by and large, we're still working up in scale. So this is still a relatively small scale endeavor. So setting the stage, which is familiar for you all, it's really exciting to be in a virtual room full of Precambrian experts. But we care a lot about how things change after deposition, because what many are interested in is what are we recording about the primary surface environment and these really fundamental unidirectional shifts that we see. So here is some compiled versions of many great plots from a lot of great work that's been done. So we've got time on the x-axis and really looking at, what's the surface evolution of the oxygen, atmospheric oxygen and oceanic or seawater chemistry. What's that like across time, and how does it impact evolution? For us, the important take home from thinking about this broader scale geochemistry is we know that there are ways that we are stratifying this water column in the deep time record, and that might create a whole host of mineral reactions that we need to be thinking about as we're thinking about primary change, all the secondary overprint that might be on top of that. And we're going to focus on iron formations for now, not because they represent the particularly best archive of seawater information, but they are abundant enough across these critical thresholds that we can really, if we can unlock a lot of the change that we see happening in them that isn't related to primary features, it might provide a great window into some of these fundamental shifts in Earth history. So I do want to highlight some previous work. So there's many amazing geochemical methods that folks have used to detangle this critical rise in oxygen, and maybe even this potential for small increases in oxygen before the initial rise in oxygen concentration. So here's just highlighting one of many very different studies, kind of focusing on tracking this oxygen record through time. And I want to highlight some recent work by Slotsnik et al. That kind of documents, looking at the same section, what's the impact of post-depositional change on some of these geochemical signatures, sort of what's that lens of complication that we might need to peel back. And so what they were finding in this study was that looking at these early and late features and really separating out and dating them and looking at their geochemical attributes, overall, maybe some of these signatures of oxygen developed later in the history of the unit. So they developed during post-depositional events rather than maybe the primary signature. So it just adds a layer of complication to how we look at these deep time archives. And another lens through which we view this an added layer of complication is thinking about what's the primary phase that we're looking at, or the set of primary phases. So I'm highlighting, there's a lot of great work thinking about how do we catalog silicate information, iron oxide information, and what comes first in any given unit. So the potential problem that we're sort of trying to provide a helpful approach to is that there's a lot of different information and data sets and redox proxies, and not all of them agree. And so where we're kind of coming at this is thinking about, is there a helpful approach that we can help with, where we can tie some of the proxy data or geochemical indicators directly to mineral and textural data to just help detangle heterogeneity, right? And if we can do that in a generalizable way, maybe we can unlock some of these complications in the deep time record. We're going to take some critical lessons from everyone's 101 carbonate sedimentology classes. So when we think about diagenesis and carbonates, we're looking at the transition into stable form, right? That includes everything from dissolution, neomorphism, replacement of anything unstable, compaction, lithification, and cementation. And so the first lesson we're going to take from carbonates is that sequential changes are trackable in assemblages if we're looking for them, and if it's not completely overprinted, right? But if we're looking at an assemblage that's not hasn't experienced too much post-depositional change, we should be able to decipher sequential changes. The second lesson we're going to take is thinking about how we use carbonate cements, how we use cements overall in a way to help us decipher an order of events, and also think about how we're cataloging the factors that are happening and affecting the rock during diagenesis. So we know that the composition of the original sediment matters. We know that the nature of the fluid that's moving through the system is also going to change things geochemically, as well as the time frame and the physical and chemical processes that are affecting the unit. So we're going to take this lesson from carbonates that we can use cement stratigraphy as a way to help us decipher order of events if we're using detailed petrography tracked with texture-specific geochemistry. And I think it's pretty reasonable to use these two lessons because when we're dealing with these samples that have different grain sizes, so up to sand or larger grains that have void-filling cement filling the space between grains, as well as mud-sized particles and different layers, we can start to track a relative order of events using the same principles we use in carbonate sedimentology. So thinking about how we're going to build or think about building diagenetic models, the first step we want to do is thinking about mapping incomplete reactions. And what I mean by that is some of these you can see in a thin section using optical light microscopy. So using reflected light, you might see differences or connections between oxide phases, the transition or oxidation of magnetite to hematite, for example. A lot of the ones I'm going to highlight are some of the ones we have a little bit less cataloging of, and they fall in the realm of the iron and magnesium silicates. And so here's just one example of an incomplete reaction that's captured. So here's the edge of a grain. And if we look in a backscatter electron image, we can see there's a connection between two phases here, right? So we can see that evidence. So if we can look at this at multiple scales and we can look at multiple samples, we might be able to see a pattern emerge. And so especially if we use tools that not only we can tell, qualitative chemical information, but we can also tell and put a mineral formula to it. So using the microprobe, we can see that that little area has variation in all of the different minerals that are present. So looking at the varying major element compositions. And this scale is by 50 by 66 microns. So we're looking at a relatively small scale. The good news, the bad news, the news is that when you look for them, these incomplete reactions can be quite abundant in some of these assemblages. And so here's just an example of a beautiful silty unit. And we've got one little grain here. So we're zooming in on that grain. And now we're going to zoom in on just one part of that little grain. It's a coated grain. And here is using the microprobe and making element maps. Here is the degree of heterogeneity in a 55 by 73 micron space. So for reference, here's the grain and the square of the area that we're looking at. So we know there's a lot of incomplete reactions happening and connections between minerals and potentially micron scale heterogeneity in a lot of places. So we want to find and map that heterogeneity, which is something we want to detangle. We need to find a systematic way that we can map that out, right? Because we can't measure everything and we can't, there's only a set number of thin sections and things you can look at for a given section across a duration of time. So what we did to kind of start detangling this is we wanted to look at where we might preserve a lot of these incomplete reactions. So we focused on thinking about silicified nodules or layers in iron-rich materials where we could see or demonstrate that this was happening relatively early, that this silica addition was happening relatively early. And so that means looking at places like this example, we've got really nice bands draping over our silicified horizons. So targeting those and as many as we can, looking across a large amount of material. And I'm pulling up some historic images because this is something that's been thought of for a really long time, that some of this cementation might be happening very early. So in this example from the Sakumon iron formation, the cement volumes and the interstitial material that's filling in is up to 40%. That's really huge, right? That's potentially evidence for this being quite early in the unit's history. And when we look at the samples, we did an XCT scan of one of these materials because they have these nice iron-rich coatings, and we see cement volumes that are that high as well. And so this idea that there is a lot of space to be filled really early, potentially preserving some of this immediate reactivity that we might be seeing. We also, like others have documented for a long time, we see competitive growth textures that are filling these void spaces. And I think we also see some interesting potential features in the units that we've been looking at where we might even have authogenic quartz coating. So this area highlighted by pink stars, we've got a little grain. It's got lots of little iron oxide laminae, but in between them or alternating with them is micro quartz, really, really, really fine grain quartz. And we also, in the same samples, will see coated pieces of cement and really fine grained chert together. And so just thinking of this as being really early processing of this material, which adds to complications later on. But so kind of pairing that, thinking about these incomplete reactions, we want to put them together in some sort of decipherable relative order of events and put some mineral formulas on them. So that's the next topic that we're going to focus on. So the way that we approached this is we were looking, remember, at those silicified horizons, but when we sampled, we also sampled any banded couplets that were next to it, so within a centimeter of the silicified horizon. And so zooming in, so here's an example of one of those thin sections. So you can see the banded texture right next to the grain texture and the silica cement filling in the space. If we zoom in on this little grain here, this grain is made entirely of greenolite as the granule material, so this iron silicate mineral, and nucleating off the edges of this mineral as a first generation cement and into the cracks inside the grain is this other silicate mineral, minnesotite. So right now we've identified a textural relationship between two mineral phases. And so what we can do then, and this is work by highlighting Sam's work again with our collaborators. So this is being able to highlight that mineral change across a transect, in this case with Raman data, but also being able to do that with microprobe data. So we can do that throughout many different sections and kind of see what is the relationship between, in this case, greenolite and minnesotite. So this is just a different example, but same kind of thing happening. We've got a greenolite grain. If we zoom into this area, we can see the same type of relationship between the two phases, greenolite and minnesotite together, and minnesotite nucleating off of that greenolite. So if we look at the microprobe data for this, what's really intriguing is that when we look at greenolite that's connected to minnesotite directly in a textural relationship, they are very, very iron rich by comparison to other minnesotite examples in the unit. So here we've got this beautiful connection, and we see a compositional connection as well. We can do that with other pairs of minerals. So in this case, here is a silicified horizon right next to a banded horizon. You can probably already see that there's some sort of reaction boundary, which we'll get to a little bit later, happening here. But what we're focused on now is the connection between the banded layer and the granular area. Inside this the silica cemented area, this time we've got mostly minnesotite. And at the edge, we've got stilbenomeline in this case. And so two silicate minerals again, but with different front ends of their chemical formula. So looking at the microprobe data again, the intriguing relationship is that when you look at these two mineral pairs, and you look at them in multiple samples in the unit, there's a connection between those two compositions. So clearly there's a documentable relationship between these phases as well, which is great news because this is now heterogeneity that we can decipher, right? So we can do this and figure out, is this a consistent relationship or is it a one-off or only part of one part of the strat column? So that's our first key take-home point, is that when we look for them, these incomplete reaction sequences occur and they're present, and we can decipher them into a relative order of events. But as with everything comes a complication. So this image here is from the same unit I was just showing you, the same drill core, just lower in the stratigraphic, in the stratigraphy. And here, instead of having beautiful silicate grains that we're dealing with, we also have these beautiful iron oxide coatings. And so in this example, we've got these really delicate cortical laminae around in mostly quartz nuclei. But here, clearly, the silicate mineral isn't the texturally early phase. Here, clearly, the iron oxides are. So kind of thinking about this as a workflow, rather than one singular paragenetic sequence, because of the complication that we have from the mineralogy, we want to construct multiple relative order of event sets, so paragenetic sequence sets that capture vertical heterogeneity and lateral heterogeneity across the basin. And so we want to basically tie the order of mineral precipitation, how that changes in a stratigraphic context. And what I mean by that is that there might be, and is likely in these rocks that we've been looking at, these Proterozoic examples, many different paragenetic sequences. So maybe you start with a relatively similar material, but whatever's proximal to that material is different, that phase that's next to different phases in different parts of the strat column. And so maybe you see a different development of a different mineral set, a different evolution, a different post-depositional evolution, if you will, depending on what you're connected to locally, if you're reactive, I should say. So what we want to do is see, okay, we've got paragenetic sequence or relative order of sequence of events A. We want to map that in multiple drill cores across a basin if we can, and try to connect larger scale what's happening with these post-depositional reactions and sort of map them out at a grander scale using mineral formula, the textural relationships between phases. And then once we have that, apply our geochemical and or isotopic data sets to try and separate out some of this mineral and textural information within a broader stratigraphic context. So I want to highlight a couple photos from one drill core. So here's from bottom to top of the stratigraphy goes from left to right. And then each of these little photos is just, it's oriented way up. And so in this unit, I highlighted some photos, not because of they show the most change, but because this is the degree of heterogeneity that we're dealing with in some of these Proterozoic assemblages. And so you can see there's textural variation, there's clearly mineralogical variation, and we want to have a systematic way to decipher that. So that brings us to the last topic here, sort of thinking about how we tie textural data to some larger scale geochemical data. And so one of the interesting things that at first that we found was thinking about, we've got these grains. So in this case, the granular photo here has greenolite granules or grains and lots of beautiful quartz cement. And then a banded example, we're looking at these couplets, right? So for any given depth, we have both a banded example and a granular example. And so this data set is showing the obvious that you can see in thin section, which is that these granular units have a lot of silica cement. Ta-da, they have a lot more silica overall. So at first, kind of trying to decipher some of this information, what we were surprised to find is that there's a little bit of clarity and clear signatures in some parts of the material versus others. And what I mean by that is, here, we've got everything oriented now on the y-axis. You've got depth, and this is just a small depth interval. It's not a whole drill core or anything, but just zeroing in on this trend at first. Here we've got aluminum, and we've got a change where we see the banded portions that are the couplet to the same relatively within 1 centimeter depth of the granular couplet that it's associated with. They record very different amounts of aluminum, which is kind of exciting in this scenario because in this unit, you're transitioning from a silty underlying unit into this chemical sedimentary unit. So this can be taken to mean it's a very nice gradual transition into this chemical sedimentary rock, which is great. But it presents some interesting questions when you start to look at other parts of the geochemical record. So I want to focus a little bit on some of the trace element chemistry, and we're going to focus just on patterns at first. So everything's not separated by depth yet, but we're just going to look at sort of similarities between banded and granular layers, and then some minerals that we see in them. So here we've got on the y-axis our sample divided by post-Archean Australian shale average by convention, and then our suite of rare earth elements plus yttrium and holmium on the x-axis. And so here from up the entire stratigraphy, from the lower, the middle to the upper unit of this example, we see banded, the banded layers or couplets. They record relatively similar concentrations of the material and relatively similar like patterns overall. There is some change with stratigraphy in the cerium anomaly, which we'll get to in a little bit. But right now, by comparison to the plot I'll show you next, these banded horizons up stratigraphy look like they are sharing relatively similar information. When we look at the granular couplets that are associated with those banded couplets, number one, it's diluted, which is expected because we've got a lot more silica. but it's also a little bit messier signature. And that can be for a number of reasons. We have some ideas about how these grains are moving and forming, but there's a lot to learn about how much they're being transported and things. So maybe this heterogeneity is because of a mechanism of formation, or maybe it's simply because of the dilution. But overall, I highlighted in the background where the banded signatures were, and they record a little bit messier, more diluted patterns. When we tried to separate out the carbonate-rich material, which is only really present in the sections we were looking at towards the upper part of the strat columns, we were able to identify that they did share some attributes with the banded couplets, which had a lot less carbonate. And so that's intriguing for thinking about what type of information the different textures might be recording. So I want to revisit that anomaly that we talked about. So this is a plot showing the cerium, kind of deciphering what is happening with the behavior of cerium. And so here, the plot is separated out by stratigraphy, but I want to highlight that it's sort of spanning the whole range of the diagram, and that's true for a lot of these Proterozoic assemblages. And so what I want to decipher next is make it into a little bit more readable format, where we can see what's happening with depth. So separating out the banded granular couplets, and where we can, where it's really abundant, the carbonate material, and sort of applying all of the critical screening that's required to see what's really representing a potential seawater signature. If we look at that cerium anomaly, the left-hand side of the diagram on the x-axis being more oxic and the right-hand side of the diagram being more anoxic, we can see that there is some potentially systematic change up stratigraphy in this particular section. And what's intriguing is that everything that's recording an anoxic signature on the right-hand side of this diagram for any depth subset is recording the same type of signature. So the fact that these banded and granular textures coexist, and that in the case of this parameter, the cerium anomaly, they're potentially recording similar types of information, is interesting when we start to think about, if we separate data out like this, what it might be able to tell us at a larger scale. So just kind of tying this together with a little bit more data, here's the same strat column on the left-hand side. And here's the same cerium plot you were just looking at to orient you. And now the next slide has the full aluminum data set. So that nice gradual trend at the bottom, and a little bit increase toward the top. But kind of looking at the data set like this, we can potentially put that together with our mineral and textural data sets to say, what's post-depositional change? Where is silica being added? Where is iron being lost? What's contaminated specifically? And is there something right close to it in terms of depth that might be less contaminated that you can analyze for looking at some of these seawater signatures? So this becomes heterogeneity that we might be able to decipher, and potentially a workflow that we can scale up. So the second take-home point is just that when we look at geochemical data and we separate out banded and granular couplets, they might be recording the same redox information for any given depth interval, but they're recording some really interesting different information for non-redox sensitive elements like aluminum. So bringing this out to a slightly larger scale, does this inform us anything about models for iron deposition in the Proterozoic? And so putting together some of the classic facies patterns and redox chemistry of this time frame, we know there's a division in the water column, and we know there's these different textures, and they're depositing in potentially different places in any given basin. So kind of putting these viewing images to these words, some of these granular and banded textures, they maybe represent shallower water, and some of these banded textures maybe represent deeper water. But bringing back and circling back to the data that we just looked at, we saw that banded and granular textures coexist, and they might be recording similar redox information. So I think the intriguing thing here is that by separating out data like this, we might be able to get pinpoint a little bit better where wave base is versus where the redox cline is, if we do this sort of systematically across the basin. The big caveat here being, we need to know a little bit more about how these grains form, and really sort of test mechanisms of formation. So circling back to mineralogy, we might be able to decipher a little bit easier some of these patterns that we see in reduced versus oxidized phases if we can better get a sense of water depth. Of course, introducing another complication that I think probably needs to be considered in this model is what happens when any of these sediments move. So if you're in a particular setting where you can move material, which we know happens, what happens if you move material quite far and potentially start interacting it with other material has a different chemistry? And the reason I say that is for a couple of reasons. One, in this particular example, we've got beautiful fluids and intraclass, and there's lots of coatings. And so here we've got two different intraclass that by the fourth time they're coated together. And so we think there's evidence for reworking in these basins, and even potentially, although it's really rare to find in a thin section, there might be some local compaction during that redeposition. So maybe there's an episodic nature to this redeposition. And so kind of zooming out to view that in core scale, here's an example where we've got grains of two different types of composition. So we've got chert granules and greenolite granules next to one another, but you can see the complicated textural relationship between them. And so we think that some of these features, if you're moving material around, it's possible you're doing some of that when the material's been sitting for a while, but it's possible that you're doing some of that while it's still relatively soft. And then it begs the question of, is it still reactive? So like chemically reactive. And so here, looking at one of these areas where we think there's potential evidence for redeposition, there's a direct connection that you see as you approach the boundary of the banded unit, in this case below the granular unit, where the granular material is predominantly oxidized, but at the contact, there's a clear reaction or there's a clear boundary between them. If we zoom in and kind of look at that at the thin section scale, this is a different example, but same principle. We're proximal to a banded horizon. So in this case, banded horizons on both the top and the bottom. You can see a reaction happening at the edge of this contact. And so in this case, locally, the bands have a little bit more aluminum when we look at the geochemistry, but overall, you're making the silicate, in this case, camosite, which has that little bit of aluminum instead of some of the aluminumless silicates that we see. So this begs the question then to the last point of how reactive are some of these materials post-deposition? And if we're accounting for heterogeneity, to what degree do we need to account for local element mobility to build this larger diagenetic framework? So revisiting the problem or the potential problem and thinking about mapping this out to a larger scale, maybe if we have this model that accounts for heterogeneity, we might be able to resolve some of the disparate interpretations of some oxygen records that we see. And so that brings me to my last point and kind of overview of thinking about how generalizable is the heterogeneity that we measure and we just talked about. So I want to revisit this set of images that shows the great degree of heterogeneity that we see in a lot of these drill core. And I just want to take home the one piece that I think is generalizable. And so just to define things, I mean universalism versus generalism in the sense that we don't want to apply a model universally to all systems because there's probably a lot of differences. But we want to work to generalize a model so that it's helpful and may apply to some additional systems. And so I think the one generalizable thing that we're pretty confident in so far is that if you look for incomplete reactions and determine the relationship between those reactions and associated cements to get an order of events and a set that works up your stratigraphy, then you can kind of tease out these mineral reactions. And if you repeat that unit by unit across the basin, allows you to detangle heterogeneity. So kind of as a workflow, this might be applicable to complicated systems where we have disparate records. So kind of revisiting and summarizing, our goal overall over time is to start scaling up. So we've been looking, I said, at drill cores across the Biwabik Iron Formation in Minnesota, and the Freedom Formation in Wisconsin. But we want to be able to really build a comprehensive framework for interpreting diagenetic reactions. And I focused here, mostly on silicates because there's so many things to still learn, but there's a lot of minerals we have to account for. So I didn't touch a lot on carbonate minerals, but there's a lot of incorporation of trace elements and things that are happening into those carbonate phases as well. So just to summarize, the key results that we have at the moment are thinking about silicified horizons might preserve multiple incomplete reaction sequences, and we can decipher them, which is great, into a relative order of events. Co-occurring banded and granular couplets might record similar redox information, but some signatures might be cleaner for other things, like in the case of aluminum, where the banded couplet was telling us this really nice gradual change. And then the last caveat of thinking about some of these materials might still be reactive for quite a while after they initially form. So local element mobility might be something that needs to be tracked when we think about diagenesis overall. And so with that, I want to thank you all so much. And I'd love to talk more with you all about questions and ideas and discussion points you might have.
All right, thanks a bunch, Latisha. It was great. Yeah, we're gonna go ahead, as you said, start open discussion. So to discuss or ask a question, you can raise your hand. And Greg will be first up. I just want to point everybody's attention to the reactions at the bottom. You click the reaction button, and then at the bottom of that expansion box is raise hand. So that's how you raise your hand, or you can type it into the chat and I will ask it for you. But please go ahead, Greg, ask your question.
Yeah, wonderful, Latisha. I really enjoyed that. It reminded me so much of something that Chris Fido is looked at quite a bit, paleosols, same sort of thing. We're looking at the paragenetic sequences with alteration. But the question I have is, in the Archean, Bolhar and others have demonstrated using rare earths, a pattern quite different from yours, that the banded iron formations were actually non-marine, now crater lakes. And of course, that's the best modern analog we have for iron oxidizing bacteria is actually in crater lakes. And I've been thinking about these big ones, like the superior type that you're dealing with. Well, that's a pretty big crater lake, but not much bigger than the Great Lakes, really. And your patterns are somewhat ambiguous. They're kind of flat. They're neither conclusive, because the paleosol pattern is to be really rich in the lights, and the C pattern is to be really rich in the heavies. Have you thought at all about paleosalinity in these banded iron formations?
Yeah. So we've thought a lot about even just being able to really tease apart, because there's so much, as you mentioned already, there's a lot of complication to some of the traditional geochemical signatures that folks have looked at to decipher some of these things. So we've been thinking about other, being able to apply other techniques. There's certainly fluid inclusions in some of these, with all the caveats that come with that type of work as well. But we don't have any right now. I mean, all of these have been interpreted as a marine depositional system at the moment. But I think there's room to revisit a lot of our, there's always room to revisit some of these depositional models, especially with a lot of the things that folks have been figuring out with potential to preserve terrestrial, terrestrial surfaces and terrestrial environments deep in the Archean. So here, we see the Sudbury in the Minnesota side, we see, Sudbury impact intervals. So kind of linking that to the marine realm, but the Freedom Formation in Wisconsin is sort of wide open. I would say there's a lot to learn there still.
No, it's fascinating. I've been concerned about marine versus non-marine because the default Precambrian geology position is that everything's marine until further notice. But there are actually lots of tests. You showed one, the highly reactive to total iron. There's also C to S ratios. There's boron to gallium. There's boron to potassium. There's a whole bunch of ways of getting at this by fairly simple analyses, actually. And I just wanted to put that idea in your head as something worth doing.
Thanks.
Thank you.
All right. I have one in the chat from K-Sender. Does the size or area of reaction horizon for a particular type of reaction remain conserved across the sample? I.e., is the size of the reaction horizon of any analytical significance, like corresponding to the depth of the redox line?
Oh, No, but I would say that it is relatively, it's maybe surprisingly consistent when you look at the scale of it. So like, here's an example. I think you all can see my cursor, right? I hope. So here,
Yeah, we can see it. Yep.
It's usually roughly a centimeter thick in any given contact point, which is surprisingly similar. So in the examples where you can see it clearly in this picture, so you can see it here on both sides, right? It's sort of centimeter scale. So I don't know that it's telling us information other than these two things don't want to be next to each other. Or there's something happening between them. I'm not sure it tells us much larger scale information yet, but good question.
So Latisha, I wanted to ask one actually. I was looking at your model towards your end, towards the end, your just sort of depositional model where you place the redox line, where you placed your granular facies and your banded facies, and you talked about having these aluminum rich iron silicate minerals, the shamosite, and you said they were kind of typically at these boundaries between your banded and your udal facies, right?
Mm-hmm. Yeah,
so
this one.
in that shift, I mean, how often do you see this shale? I mean, if it was this shale kind of interlayering in here where you're seeing your where you have your shale placed between the banded facies and the oolitic facies. And also, I guess, I mean, it's interesting to me because maybe this is sort of an expression where, you maybe had too much energy to really deposit it, but you do finally have a situation where you can sneak those aluminums into the silicate minerals. I mean, a lot of the time you really just don't see that in these. The shamosite, that shamosite is mostly expressed in Phanerozoic ironstone. And I'm not really getting to a question, I guess, but what is your interpretation of that, I guess?
Yeah, I mean, so it surprised me when we found more camosite than I was expecting. But then when you look back, I mean, folks have certainly documented it before. We're not the first to do that. But it was sort of, not lost in the discussion of it. It hasn't been brought out as a prominent feature. But I think there's a two-part sort of interpretation of that. When we look at these banded layers, we kind of group, maybe we don't, but it seems to me we often group them a little bit as like they look like this is the banded part of the banded iron formation. But I think there's a lot of sneaky detrital material, and converse, I think there's a lot of authogenic material in some of the, or you can flip it, I suppose. There's authogenic material mixed in with some of these detrital units that maybe at first glance look like they're part of the iron formation, but there's a lot more detrital material in some of these, but only specific to the banded horizons, which is probably speaking to some nature of how that silica is being added, or the timing of that. But yeah, I think we found a lot more camosite, and it's not just in like, in this case, the lower part of the stratigraphy where we see that clear aluminum signature. We see it even when it's not a measurable aluminum signature in like the whole rock sample. So it becomes alarming a little bit in thinking about how that might be impacting some of the seawater geochemical record.
Yeah, I just in my head, it's just so interesting that we see so little aluminum in these, and then here we have the shamosite kind of in between the two types. And it's been making me think a lot about the aluminum questions here. So I was just curious to hear you say a little more. Thank you. Andre, did you want to talk?
Yeah, I have sort of one comment on what you, Alex, and Latisha just discussed, and one question. So, I mean, if granular is high energy, wouldn't you expect that sort of clay material would be washed out into deeper environment, into which would be bended, and so it's sort of a natural result of sort of hydrodynamics in a basin that you would be transporting clay into a deeper environment, and it would be associated with banded layers. So that's just a quick comment, and then maybe I continue with question. Okay, you agree with it? Okay, so a question, it's sort of not exactly related to your talk, but kind of somewhat related. So, was a lot of discussion recently, what were primary minerals or sort of what precipitated iron forming either banded iron formations or granular iron formations. And so we kind of the question like what were most abundant minerals, and where people approach it in a similar way like you do, like in metamorphic petrology, you look on paragenesis and what's the most early phase. But to some degree, the answer is, so this approach doesn't really answer this question, because what you're getting out of it, what were primary minerals, what evidence for primary minerals in precipitation. But if you have a number of minerals and some of them more reactive and they would disappear, and you preserve less reactive, it doesn't necessarily answer what were the dominant iron precipitating minerals. So for example, if you have iron oxides and iron silicates, and iron silicates for some reason preserved better, you will destroy evidence for primary deposition of iron oxides. But it's still possible, even if you find in any iron formation iron silicates, that iron oxides were primary precipitates, but they were just destroyed through later reactions. Do you have any thoughts about it, or how we can approach it?
Sure. So it's certainly a very complicated question that a lot of folks are doing a lot to work on. So, I think the experimental work that Jenna Johnson and colleagues are doing will help inform what's possible to make as primary precipitates, and that will certainly give us a new lens with which to view these types of materials. I think in short, so the most abundant phases in these, we have actually full core scan and mineral logs for all the drill cores that we were looking at in Minnesota. And I mean, the most abundant mineral is magnetite and quartz, but the magnetite is really overprinting a lot. But I mean, the iron is coming from somewhere, and there's a reaction. We can document some of the late reactions with magnetite. But you're right, there's always the possibility that everything you look at is such that you never preserve any of the earliest reactions. That's always a possibility. I think for us, what we're really focused on is if we can start to put together all the possible mineral reaction sequences that we see, tie it to abundances, and start to calculate volumes of change, like volumes of reaction, like the actual volume of change that's occurring between the redox states. So applying Zanes and tools to some of these materials and being able to say volumetrically, we see this much change of iron 2 to iron 3 across these different reactions and look at the scale. I think then we might be able to tell and see what's feasible, right? But as with any type of work that deals with complex reaction sequences, there's always the possibility you've wiped out everything that was first.
Thank you.
Okay, Phil Freilich, go ahead, please.
Okay. Oh, I guess I should put my picture up. Sure. There.
Hi, Phil.
I just wanted to comment on the aluminum sort of problem. Up here, for people who don't know, I'm just on the other side of the border on the same unit. But up here, we have to have sort of a different sequence because we're much more sure proximal here. And so what we find here is that, about 50 meters above the base, there's a nice stromatolitic layer. And then above the stromatolitic layer, we've got 20 to 30 meters of shale. And it's just a nice pure shale. And you sort of lose it as you go up through when you start getting more and more chemical sediment layers in it. But I had one of my grad students sort of trace it down using the drill holes, the MGS holes in the states that you're probably using. And he could see the shale mixing in with the chemical sediments as you go down. And in fact, what the miners down there term the lower slaty unit and the upper slaty unit, up here, they're two shale layers, quite thick shale layers. The top one is near the top of the sequence. It's a lot thinner, with the 150 to 60 meters up. It's a thick one. So there's no problem getting aluminum delivery. In fact, we've got accretionary lapilli in the stuff. We've got the basaltic flows that correlate with it just north of the border. So there is that influx. The interesting thing is that the bottom 50 meters, we find that we don't have really much evidence for aluminum in that bottom 50 meters up here at all until we get into the eruptive event that the shale is actually an ash. The eruptive event that puts the ash down, that's why it has accretionary lapilli in it. And then it goes down to the sill. So I was interested in your plots that you seem to be picking up reasonable amounts of aluminum in the bottom 50 meters, which is quite different than we have up here. So I'll just throw that out.
I do wonder about the synchronicity of the deposits. You know, maybe we're capturing a little bit of a prelude to what you see up there at the basal part of the section, which would make sense.
Yeah, and we do see that with the shale coming in, because up here the shale sits right on the stromatolitic layer, but when you go down across the border up into the Gunferlin Trail just across the border, there the shale is about 2 meters above the stromatolitic layer, which makes sense because here if we're near the shoreline, stromatolites are near the shoreline. Stromatolites were there before they were here, so by the time the stromatolites developed here, you got nice grainstones on top, and then the shale comes in. So there is that difference, but it's not that much of a difference that we see. And of course, there's not a whole lot of time layer units in it, so you can't really do that much. But anyways, I'm going off on tangents now, so I'll shut up.
Yeah, it was interesting, Phil, that you mentioned that they're actually that the shales are actually related to volcanic input, because that makes it all of a sudden an event bed rather than, you know, something that works with sequence stratigraphy and that sort of model. So for me, the way I've been thinking a lot about this shamosite, the difference in iron silicate mineralogy and iron-rich rock, you know, sedimentary rocks from the Precambrian to the Phanerozoic, and you see this shamosite and more primary textures and Phanerozoic stuff. But here, you know, here in the Precambrian, when you get these things that, you know, these cortices that look like they can be primary oolitic in these granular iron formations, they look like they're alternating between an oxide phase and just a pure, clean, cherty silicate. I mean, and you see that in banded too. I mean, it seems like it's similar 1-to-1. So it's almost like, it sounds like aluminum was pumped into the system that wouldn't in excess rather than being regular, you know, trickling of aluminum. So I'm just wondering if aluminum was lower in these depositional settings unless you pumped it in at a high rate. So that's
sure.
cool.
Thinking about sources,
Mm-hmm.
where it's coming from.
Yeah. Okay, I don't really have any other questions. Kay Sender sent another one. Do these rocks retain any sort of paleomagnetic signal? If yes, does the incomplete reactions and heterogeneity affect this anisotropy?
That I don't know, but would be certainly interesting to look at. I'm not sure if there's been a ton of paleomag work on the units, but others would probably be poised to answer that better. But to my knowledge, I don't know.
Greg wanted to chime in again. Go ahead.
Yeah, this discussion of alumina is very interesting. It's not a very large amount, really, is it? Up to 3%. That's pretty pathetic when you think about it. But the fact that it's more abundant at the very bottom suggests to me that, hey, maybe there was soil formation down there that the clay is coming from. The fact that it sort of spikes at 2 levels higher than that, is there any evidence of a hiatus in sedimentation that could be a soil forming interval?
Yeah, so I think one thing we've been really discussing and trying to get better dates in these successions is that I do wonder a little bit, and as do my colleagues, about whether or not there's more than one unconformity. I don't think they're hugely separated in time, but there's definitely the possibility that there's gaps that exist.
Yeah, it's not much a limit to explain, really. But soils are the main clay factory. Yeah, that's pretty striking at the bottom there. You showed another one later on too that had it. Oh, you've got the slight increases at near the top, and yeah.
Mm-hmm.
Oh yeah, look at that. Yeah, this is nice, isn't it? Yeah. Usually when people make formation boundaries, or even lower, middle, and upper, there's some lithological change that corresponds with some sort of a break.
Yeah, I should maybe clarify. There's boundaries that pre-exist our work. And so I am acknowledging those boundaries. I did title them slightly differently because of there's a lot of everything. This is the lower Cherty, lower Slaty, upper Cherty, and upper Slaty that correspond across. I do think we need probably new division lines that link to some of the geochemical or like the lithologic change that we see linked to the geochemical change.
Yeah, the old geologists, they had a good eye for change, and when things changed dramatically in the Badlands of South Dakota, I remember this quite strikingly, Oligocene, the formation names corresponded to whole suites of paleosols, and each formation had a hiatus between it when everything had changed, and that's why the general appearance of the rocks was so different. There's meaning to these differences that may seem arbitrary at first, I think.
Well, and I should note that these they're good boundaries in that they really correspond to visual changes across most of the units we see in Minnesota. So they're really serve as great boundaries as a starting place to say there's probably change to look for across here. Our sequence too, we could do more detailed. We have a pretty sparse, for a stratigraphic context, we have a pretty sparse data set geochemically up stratigraphy.
Right. No, these are good points. The lateral continuity means something. Absolutely. Mm-hmm. Yeah. Thanks again.
Okay. Yeah, Max Lecty says great talk. I don't see anything else in the chat here, so, or any hands up. So I think it's time to thank you very much for being on today. Really, really good stuff.
Thank you all.
Next week we have a talk from Sylvina Slaughter from Yale University, talking about experimental constraints on Ediacaran style preservation. So if that's exciting to you, we'll see you next week. All right, everyone, take care. See you all later.
Thank you all.